In this video, I'll be covering chapter 2 of Campbell Biology. So first is some concepts that were talked about in the last chapter. This is chemical foundations of biology. Living organisms and the world they live in are subject to the basic laws of physics and chemistry, and lives have different structural levels, and different emergent properties appear at each successive level. So the first topic is about how matter consists of chemical elements in pure form and in combinations called compounds. Organisms are made of matter, and matter is anything that takes up space and has mass. Matter is made up of 92 naturally occurring elements, and out of those 92, 25 are essential to life. Out of those 25, 96%, I think it's by mass in like all living things, is made up of CHON, or carbon, hydrogen, oxygen, and nitrogen. And the remaining 4% by mass is mostly calcium, sulfur, phosphorus, and potassium. And those like minerals that I just listed are called trace elements. Trace elements, basically majority of them are, or I think all of them are basically minerals. And trace elements, for its definition, is elements that are necessary to life except in like small amounts. Just because they're necessary in small amounts doesn't mean they're unnecessary. They're still necessary, but in small amounts. That's in the definition. And then things I skipped over. In the sentence for the topic, it says matter consists of chemical elements in pure form and in combinations called compounds. So if you have like an element and then you combine to two of them or something, more than one, then you get a compound. And then next topic is 2.2 on an element's properties depend on the structure of its atoms. Atoms are the smallest unit of matter that still retains properties of an element, and it consists of subatomic particles. There's 3 subatomic particles: protons, neutrons, and electrons. There's a diagram here as well. And these 3 subatomic particles are separated into 2 different regions: the atomic nucleus and then the electron rings. And it's also visible on the diagram here. So over here is a nucleus, and then outside there's like these different rings, and then those are the electron shells. It says shells right there. And in the parentheses there are like the charges. So the protons is +1 charge, neutrons is 0 charge. It's easy to remember to think, or if you think about how neutron sounds like neutral, so neutral charge, 0 charge. Electrons are -1 charge. And we'll get more into charges in a second, but we'll talk a little bit more about the atomic nucleus. The atomic nucleus is made of protons and neutrons, and it makes up basically more than 99% of the mass, because the electron's mass is severely, like, it's insignificant compared to the mass of the protons and the neutrons. Next, the atomic protons and neutrons combined make up the mass number. So the atomic nucleus is the protons and neutrons combined. So the atomic nucleus makes up the mass number, and it's because electrons don't have like a significant mass. Like I don't remember the exact number, but if you look in the textbook, I think they give you like how like the exact like magnitude of how small the mass is, but it's basically just really small. And then next, the number of protons make up the element number. So for example, hydrogen has 1 proton, and if it has more protons than that, then it's not a hydrogen anymore. And the next is difference in number of neutrons make isotopes. So difference in number of neutrons means like there is a specific for each element, there's gonna be a specific ground states number of subatomic particles that it should have. Yeah, sure, you can and then if it has like a unusual number of neutrons compared to that, then you would call it an isotope. And then next is we'll be talking about electron rings, which are basically these different shells or levels, and electrons occupy the space. And talked about the electron mass. And then so next like concept is how opposite charges attract and then same charges repel. And this means that protons and electrons if you put like a proton and a proton together, it would repel. And if you put an electron and electrons together, they repel each other. So you can actually kind of see that in this model of the atom, in which you see that how in the nucleus, oh, like the protons are not they're kind of separated by the neutrons, and which is actually like the role of the neutron in within the nucleus, because without it, it would be like unstable. So I think like in like a ground state hydrogen, you actually don't have a neutron because you don't really need it because it's just one proton, so it's not gonna repel anything. But afterwards, like neutrons are become necessary to keep the nucleus stable. And if you're curious why the protons and the electrons, even if they're the opposite charges, like they're separated by different regions, right? And why that is because electrons are like really like hyperactive. First of all, like the mass is like super small, and it's like kind of crazy. Like it's really chaotic. So these two, like even if they technically like attract each other, like you'll see how like the opposite charge attraction thing works when it's between an atom and like another atom, but within like just like a singular atom's like level, like within that atom, like the protons and electrons don't like attract towards each other. Like they are technically attracted because the electrons can stick onto the atom because there are like protons there, but they can't exactly like stick together because the electron is so like unstable. But there's technically still like a attraction going on. And then next is how overall charges for the atom works. It's basically minus or one electron plus one proton is neutral charge, and atoms tend to like neutral charges, which we'll get into more in a second. So this is the next slide where we continue talking about 2.2. Excuse me. First, radioactive isotopes. So isotopes, if we review the definition from the previous slide, is a atom with a unusual number of neutrons. And radioactive isotopes are specific isotopes that are unstable and decay spontaneously. And by this, it means like they emit particles and energy. And sometimes these radioactive isotopes, as they decay spontaneously, they could be like illuminating. So this could be useful in many ways because first, it's regularly used as a type of marker, quote unquote marker, because it especially like the ones that like illuminates or like glow, I guess, or could be like tracked visibly, because let's say you want to track how like bodily functions work, like I don't know, maybe you want to analyze how like bloodstreams work for some reason, and then how one like I guess like you injected something to the person's bloodstream and you want to see where that how the bloodstream like flows. Like if you want to check how that stream flows, then you can inject some like illuminating radioactive isotopes into that person's bloodstream, which is probably like not good for their like health, but let's just say theoretically, then somehow you can get that person like see like their analyze or look at their bloodstream under like a microscope, that allows you to like track where the radioactive isotope is like going. Then it would like let you track where it's going. Just refer to like the example in the textbook if you want to know more about it. I don't think it's like necessary for you to like this information is not as important for AP Bio students at least. And the next, radioactive isotopes decay at a constant rate, which is why they're so useful. So what I mean by this is they have a constant rate in which they like decay by half. So let's say the half-life of element X was what is it, like 10 years. And just for the sake of explaining, let's just say that half-life was based on mass. So element X's like half-life is 10 years. Let's say we had 4 grams of element X, or radioactive isotope X, initially, and then after 10 years, what's going to happen to that isotope's mass is that it's going to go by half. So it's going to be at 2 grams. And then after another 10 years, it's going to be at the half of that, which is going to be 1 gram. And that's basically what a half-life is. And we use this constant rate to figure out fossils, like how old fossils are, by tracking the radioactive isotopes inside them, and then like tracking like how old they are, or like how much they've decayed. And then if we figure out how much they've decayed, then we can figure out how much time has technically passed, because their half-life is consistent. I think there was like a little activity that you can do in the textbook, so if you want to check that out, be sure to. But this information is also not as important for AP Bio. And then next is on electron configuration. Electrons occupy like different shells. Shells have an order to, I guess, how they're occupied. So in this model of the atom, when electrons like fill up these shells, it's gonna be the first shell, like the innermost shell first, and then the next, and then the next one. That's what I mean by order. And they also have a limit to how many electrons could sit in one shell. And so basically, the first shell, the innermost shell, is an exception, where the max limit is 2, and then afterwards, each like valence limit is 8 electrons. And then next, the valence shell is the outermost shell. It's the outermost shell, yeah. And then the number of valence electrons determine the reactivity of an atom. And this is because a reactivity of an atom, you can basically think of it as reactions with like different like charges, I guess. Like, because a valence shell is, or in the outermost, or after the innermost, after the innermost shell, the valence shell limit, or the electron shell limit is 8 electrons per shell. And for an atom wants to achieve a state where the valence shell is completed at 8 electrons, because that's when the atom is most neutral. And because of that, that's like their goal, right? And so to achieve their goal, these atoms are going to react with different atoms in which maybe they share different electrons or give away their electrons to reach a state where their valence shell has 8 total electrons. And we will go over that right now, actually. So 2.3 is on the formation and functions of molecules depend on chemical bonding between atoms. And so reactions between atoms is sharing or transferring of incomplete valence electrons. And below are the strongest type of bonds. Bonds are created through reactions between atoms, by the way. And so the sharing of electrons, we call it a covalent bond. And these covalently bonded like atoms create molecules. Next is when you transfer electrons. So an atom gives away an electron or takes away an electron from another atom. And this causes ionic bonding due to charge differences, because now the atom that gave away one of its electrons is going to have a +1 charge, for example, and then the atom that took the electron has one more electron. One electron is -1 charge. So now the atom that took the electron is going to have a -1 charge. And the overall charges will make them want to stick together, or they will make them attract each other because their overall charges are opposite charges attract. And when you have ionic bonding happen, you create an ionic compound. Bonds form in a way in which atoms can complete each other's valence shells best, which is what I just talked about, like in the previous slide. And then even when electrons are shared covalently, it can be shared unequally, in which an atom's electronegativity is much more higher than the other atom. Electronegativity is a term we use to define an atom's, like, I guess think of it as like the more this atom like can pull, like wants an electron, the higher its electronegativity is. So you can think of electronegativity as an atom's pull for like another electron. And unequal covalence is polar. I'll show you a diagram in a second. And poles are indicated via this sign. It's called a delta sign. It's a lowercase delta. And then equal covalent bonds creates a nonpolar molecule. This is a periodic table of elements. And then I forgot which one of these are the 92 naturally occurring ones, but basically, yeah. There's like ways for you to read the periodic table, but I'm not gonna go over them. But it would be really handy for you to know how to like read the periodic table based on like the different trends, because then it's going to make it way easier for you to understand patterns with how, like, why some elements react in like a similar way to each other. I might make another video maybe on that if I guess I feel like it. But yeah, but this is a periodic table. Yeah, just wanted to show you that. And then here are, so the water molecule over here, this is H2O. This is a molecule. It's right now they are sharing. This is a covalently bonded molecule. And then you see like the delta minus and the delta plus signs. So the oxygen here has a stronger pull for electrons. So electrons orbit, right? And these guys are currently sharing electrons right now. However, like when they orbit, since the oxygen's electronegativity is way stronger, as the hydrogen's electrons like orbit around here, it's gonna want to stay longer on the oxygen side, and this is going to create a temporary charge where it's like a slight charge that the oxygen has, where the oxygen molecule or atom over here is going to tend to have a more negative charge, and the hydrogen atoms over here is going to tend to have a more positive charge because of the electronegativity differences. And then over here is an example of like an ionic compound. And so over here, it's a salt. It's a salt crystal, which is made of NaCl. And Na and Cl, when they react with each other, Cl wants to take away an electron from Na, and then Na wants to give an electron to Cl. And so what happens is, after they transfer electrons, Na is going to turn into like these two are going to turn into ions. So the salt Na, or the sodium, is going to turn into Na plus, and the chlorine is going to turn into Cl minus. And then this like charge difference, it's Na plus and Cl minus, right? These are opposite charges, and they're going to want to attract each other, and then they're going to stick to each other in this structure that we call a lattice, and this is what we call an ionic compound. 2.3, continuing on, I think. Wait. Oh yeah. Yeah, continuing on, weak chemical bonds play important roles in the chemistry of life. And so this is going to be a third bond that we're going to discuss, and it's called a hydrogen bond. And hydrogen bonds are weak bonds that form due to charge differences, or temporary charge differences, because it's relating to the partial like delta minus, delta plus, like temporary charges. Weak bond that forms due to charge differences between an already covalently bonded hydrogen in a polar ray and another highly electronegative atom, for example, like water. And so, do I have... Okay, I don't have a diagram. Gotta quickly get it, actually. molecule. It's kind of funny. Okay. Let me just get like a random diagram. There we go. Okay, this is good. Okay, so if you see in this diagram, basically hydrogen bonding occurs because there are like polar molecules that can form from covalent bonding, such as what we saw with water. And so what we see here is basically the hydrogen over here. It has like a slightly positive charge, right? And that slightly positive charge is reacting with the slightly negative charge of an oxygen of another water molecule. And this is an example of hydrogen bonding. So yeah, there's that. And then next, another weak bond is called van der Waals. What is it? Forces, or you can call it's also the same thing as London dispersion forces. It is a series of faint charge related bonding that happens between atoms because to explain this, it's basically like even within like a neutral atom or molecule, as electrons like orbit, there can be moments where electrons are like congested in like a specific area, which causes that area of the atom or molecule to gain a like partially negative charge, and that partially what is it very temporary partially negative charge or partially whatever charge, like that partial charge could react with like another atom or molecule that happens to have the same temporary charge, except it's like the opposite charge, if that makes sense. But you don't really have to understand how it works if you're in AP Biology. I think you go over it. Yeah, you definitely go over it in AP Chemistry, though, or more in depth, but it doesn't matter that much. And this force, hydrogen bonds are like more stronger because these are like induced by the covalent bonding and the atom's like electronegativity that's involved within the covalent bonding. But for van der Waals interactions, like it can happen even between like non-polar molecules, for example. And basically all atoms and molecules can have or all have van der Waals forces. And this is the force that's responsible for creating surface tension. And next, molecules have different shapes depending on how they're bonded, and this impacts their function. Common theme on biology is that shape determines function, and so you should know that. Yeah. And then hence molecules with similar shapes have similar biological functions. And so this is called a Vesper chart, but it basically shows you how molecules could take on different shapes depending on their electrons, how many like electrons or electrons they have, and how many like atoms they have linked to it if it's like a molecule. So molecule. So basically, I'm not gonna go too deep into it, but if you're taking AP Chemistry, you will learn about this. But you don't really have to know about it if you're taking AP Bio. And then I don't think the textbook goes that in depth into it either. And then 2.4 is chemical reactions make and break chemical bonds. And so in a chemical reaction, we have reactants and products. And the starting molecules are the reactants, and the final molecules are the products, which we can see in the formula. And atoms cannot just like randomly get destroyed or disappear. I think that's a second law of thermodynamics, but that's just one of the natural laws, and hence reactions must be balanced. And if you see in the glucose to like carbon dioxide, water, and energy, what is it? Reaction over here. This equation is balanced because For example, what it means by balance is like the atoms the atom numbers, the number of atoms on each side are equal. So, for example, on the reactant sides, we have 6 carbons, and then on the product side, we also have 6 carbons. And then on the reactant sides, we have 12 hydrogens from the glucose. And then on the product side, we also have 12 hydrogens because one water molecule has 2 hydrogens and there's 6 of them. So that makes up 12 hydrogens. And so that's what balanced reactions are. Most chemical reactions are reversible, and some go to completion, which means the reactants completely turn into products. Reversible means that reactants turn into products, and products can also turn into reactants. A chemical equilibrium is a state where the rate of forward reactions where reactants turn into products and reverse reactions where products turn into reactants are equal, and this makes the net increase of the reaction 0. So on the outside it looks like, oh, like there's nothing happening, but there actually still are reactions happening, either whether it's from reactants to products or products to reactants. It's just that the rate of those two reactions have equalized so that there is no like net increase of reactants or products. And usually the chemical equilibrium, once it happens, is what marks the end of a chemical reactions. It means the chemical reactions has like finished. There's like nothing more to observe. And all chemical reactions have a set rate or a ratio of reactants to products it wants to achieve depending on its environmental and elemental conditions. I don't think this is important for the sake of AP Bio, but you'll learn about it in AP Chem. There's a lot of stuff like that. Okay, this video was longer than I thought. Thanks for watching. If you have any questions or any mistakes I've made in the video, feel free to comment, and that would be a lot of help. Okay, thank you.